When we started talking about bonding, we said that atoms could do one of two things in order to achieve the octet rule, in order to get that full outer shell of valence electrons. We said they could either transfer electrons, which is what we talked about with ionic bonding, or they can share electrons. And sharing electrons is called covalent bonding, a sharing of electrons between atoms. And while ionic bonding is going to be happens between metals and nonmetals, covalent bonding happens just between nonmetals, at least for the purposes of this class. If you have any engineer parents out there, they may go, well, that's not exactly true. But for the purposes of this class, covalent bonding is sharing between nonmetals. All right, so let's look at a couple of examples. Let me preface this by saying I'm going to be putting some diagrams up here, and I do not expect you to be able to draw these diagrams. This is something that we'll get into a whole lot more in chemistry, so I'm going to try to explain why it happens the way it does, and then I'm going to teach you how to name them. And for covalent compounds, that's really the easy part. So I'm just going to try to show you what happens here. We're going to start with hydrogen, and even though hydrogen is over on this left-hand side of the periodic table, some people say it should actually be right here on the periodic table instead, because in some instances it kind of behaves an awful lot like these guys here, where it has an extra electron and it really just wants to get rid of that electron. It could gain another one to look like helium, but what hydrogen normally does is it normally loses an electron, which is why we stick it over here. So hydrogen's kind of a weirdo. And you'll notice in your periodic table, when they have everything kind of color-coded as to the different classes that it's in, hydrogen is gray, and it is the only element that is colored gray, because it's in kind of a class by itself. So normally on a periodic table, you're going to see hydrogen here because it wants to lose an electron, but hydrogen is not a metal. So I want to make sure you understand that. So hydrogen has one electron, and what it really wants to do is it wants to look like helium. And helium has how many electrons? Remember, helium was different than everything else in this column because helium only has how many? It only has 2. So hydrogen, if it gets next to another hydrogen, and the other thing that I'm going to do here is when you're drawing these kind of structures, you can kind of switch around what side of the box you put the electrons on, in order so that you can make pictures that aren't so messy. So I'm going to take hydrogen's electron, I'm going to stick it on this side for this particular atom. Well, they each want one more, but neither one of them wants to give up his electron necessarily. And so in this particular case, what they're going to do is they're just going to kind of share these 2 electrons between them. And when they do that, I have a hydrogen molecule, which is H2, because this hydrogen gets this one part of the time, and this one gets this one part of the time. They're sharing it between them, kind of like when 2 kids share a toy. You have it part of the time, you don't have it part of the time, you play nicely with it together. So H2 is an example of a compound when electrons of this, or when atoms of the same type bond with each other. All of the compounds we looked at the last couple of days had 2 different types of atoms bonding to each other, but now we've got the same types of atoms bonding to each other. So what happens with something like oxygen? Oxygen has 6 electrons, and I'm going to do the same thing here. I'm going to kind of rearrange the electrons on the side that they're on, just so that my picture's not quite so messy. So with oxygen, what happens is that they're going to share this electron, or these electrons, and they're going to share these electrons. And so when they share these electrons, this oxygen now has 1, 2, 3, 4, 5, 6 of its own, and it's sharing this one, and it's sharing this one. So at least part of the time, it has an octet of 8 electrons around it, and this is the same way. It has 8 electrons around it as long as it can share the 2 electrons on this oxygen. And so that's why oxygen, the oxygen in the air that we breathe, is O2, because these 2 oxygen atoms will hook up to each other. They'll bond to each other. Because remember, why do they do that? They do that because they're more stable that way. Their desire to look like a noble gas is satisfied because they now have an octet of electrons around them. so they're going to share electrons. Nitrogen does a very similar thing. Nitrogen has 5 valence electrons. Remember where it is on the periodic table. So if I draw 2 nitrogens here, nitrogen needs how many more? It needs 3. So they share these 2, and they share these 2, and they share these 2. And when they share them, then they're going to end up with 8 electrons around it because they have 5 of their own, plus 6, plus 7, plus 8. Okay, so I add that. Now each nitrogen has its own 8 electrons. It's sharing part of them. And so nitrogen, also nitrogen in the air is N2 because 2 of them are always hooked together because they are more stable that way. Okay, so there are several elements. In fact, there are actually 7 of them that hook together like this so that they are more stable. But I don't have to have covalent bonds only between the same elements. I can have them between different elements as well. And because you're so familiar with water, this may look familiar to you too. Again, I'm going to kind of rearrange how I do this a little bit as far as where I put my dots so that I can make a nice, neat picture. Oxygen has 6, and we already talked about how hydrogen has 1 electron. And so this is not going to be an ionic bond because these guys, I don't have any metals. Metals are the ones that want to give up their electrons, but the non-metals and hydrogen tend to want to gain another one so that they can look like they're noble gases. So they're going to be more likely to share in place of just giving something up. So this hydrogen will share an electron with the oxygen. This hydrogen will share its electron with an oxygen. So now when this sharing takes place, this oxygen has 8 electrons because he's sharing this one and this one. The hydrogens are each sharing 1 electron from the oxygen, so they now have 2 electrons around them, which causes them to look like helium. Remember, helium only has 2. And so therefore, the formula for water is H2O. Okay? And this is what's going to happen in a whole lot of different compounds. I'm just going to show you one more. Again, I don't expect you to draw these kinds of structures. I just want you to understand what's happening, how they are sharing electrons so that they will have an octet around them. Carbon has how many valence electrons? We've not done much with carbon. Yeah, it has 4 because it's in group number 14. And so it's got 1, 2, 3, 4. Well, what's it going to have to do? Well, it's either going to have to gain 4 or it's going to have to lose 4 in order to look like a noble gas. Your nonmetals usually want to gain them. So what am I going to do if I want to bond it with maybe another nonmetal? How about chlorine? Chlorine has 7 valence electrons, so I'm going to put 7 around it. And so this chlorine can share that electron with that carbon. And now, is that chlorine happy? Absolutely. He has an octet of electrons around him. My carbon's not happy yet, though. So let's stick another chlorine over here. And here we can share that one. And that chlorine's now happy. My carbon still isn't happy because he only has 1, 2, 3, 4, 5, 6. He still needs 2 more, right? So I can take this chlorine and we can share this pair. So this chlorine's happy. My carbon's almost happy. He's just 1 short now. So now this chlorine has 7 and he wants to share 1 more here. So each chlorine is now sharing 1 electron with the carbon. So each chlorine now has its own 7 plus the one it's sharing. That makes 8. So he's obeying the octet rule. The carbon in the middle started with 4 of its own electrons, and it's sharing an electron with this chlorine, with this chlorine, with this chlorine, and with this chlorine. So he has 4, and he's sharing 4, so that makes a total of 8. So now he's obeying the octet rule. He looks like a noble gas, and he's happy as well. So we can get all kinds of really complicated structures depending on how many atoms we're going to share and how many times they're going to link up to each other. Again, a lot of that is a subject more for chemistry. But when I do this, my formula here is going to be Cl4, 1 carbon and 4 chlorine. So the formula looks a lot like they did before. What I want you guys to know how to do is if I give you a formula like this, I want you to know how to name it. You're not going to necessarily you're not going to have to draw any of these structures like this. I just wanted you to see the pictures so you get an understanding of what's happening. All right, in order to name these, you need to know these 6 prefixes. And if you want to write them down and put them on an index card, and if you even want to use that index card on your test, I am perfectly fine with that. So you can make sure you tell your folks that when they give you your test here in a day or two, that Mrs. Thompson said on the video that I could use my index card that has these prefixes on it for the test. So you can use this and you can use your periodic table on the test. So mono is the prefix for 1, di is the prefix for 2, tri is 3, tetra is 4, penta is 5, and hexa is 6. So if you want to pause the video for a second and get an index card and write down this information right here so that you'll have that, that would be a good idea. And then once you get that written down, come back and I'll show you how to use it. Okay, so we started out today, well, I started out with some diatomic molecules that were just the same, but I'm gonna look at water first. Now we know this as water, but if I wanted to name it appropriately, what I would do is, just like when I named the ionic bonded molecules, I'm still going to use the name of this first element, but now I have to look at how many atoms of each one I'm going to use, and that's where the prefix comes in. So since I have 2 hydrogens, I'm going to use the prefix di. So this is going to be dihydrogen. And just like before, I'm going to put an IDE on the end, and when we used O before, we know that it was oxide, but anytime I have covalent bonding, I have to use prefixes. And the reason for that is because I can combine nonmetals in different combinations. They don't have the charges. I don't worry about the charges like I did before. So sometimes I might have different numbers of these atoms in different molecules, and the only way for me to know how many is by using the prefixes. So since I have 1 oxygen, I'm going to use mono. So I'm going to have mono oxide, except I don't want to say monoxide because that's hard to say. So it would be monoxide. So you've got your prefix on both of them, and this one is just the name of the element, and you have to put an IDE on the end of what you're naming. Hopefully that wasn't too complicated. Let's do another one. Let's say that we have CCl4. I just drew a picture of that one, okay? Now, for mono, I don't have to use mono at the beginning. So I'm actually going to stick a little note on here. Mono, not on first element. Okay, so I just have 1 carbon, but I don't have to say monocarbon, because if I just say carbon, I'm going to know that there's only 1. You always have to put a prefix on the second one, though. You don't have to put one on the first element if there's just 1, but you always put a prefix on the second one. So this is chlorine. How many of them do I have? I have 4, and 4, the prefix that I use is tetra. So I'm going to use tetra, and it's chlorine, but remember it has to end in IDE. So it's going to be carbon tetrachloride. Carbon tetrachloride. Okay? How about something that looks like this? Now this one might actually look familiar to you because we inhale oxygen, we exhale what? Carbon dioxide. Well, where did that name come from? Well, CO2 is the formula. Carbon, remember I said if you just have 1 at the beginning, I don't have to use mono in front of it. If I have a di, or if I have 3 of them, then you have to use a prefix. But if you just have 1, you can just use the name of the first element. That doesn't work for the second one. Okay, now how many oxygens do I have? I have 2, so the prefix for 2 is di, so it's going to be carbon dioxide. Okay, so again, just like before, everything has to end in IDE, and you have to make sure that you get your prefixes on there. The only time you do not use a prefix is on the first element if it is mono. That's the only time that you would not. Okay, how about if I had this one, N2O3. Nitrogen, how many of them do I have? 2. Okay, 2 is di, so it's going to be di nitrogen. And then what do I have here? Oxygen means it will be oxide, and the prefix is 3, which is tri, so it's going to be trioxide. So again, prefix, name of the element, prefix, name of the element, but with the suffix IDE, okay? One more. How about if I do BF3? What's that? Well, what's that element? I'm not sure we've done a whole lot with that one, okay? That one's right up here. That one's called boron. Do I need a prefix? I don't, because it's the first one and there's only one of them. So this instance is kind of like this one here, where I can just write boron because I just have one and it's the first one. So boron, what's this? It's the element fluorine, and it's going to end in ide. How many of them do I have? 3. So I have to use the prefix tri, boron, trifluoride. So here's my IDE, here's my prefix, and I don't need a prefix here because I just have one. All right, so you will have some practice today working on naming covalently bonded compounds.